We're going to start off the section talking about different groups of numbers, and we see here with our notes that we have several different types of numbers, and all the numbers we're going to be talking about today belong to this big set of what's called real numbers. And we see that the real numbers is a set of all rational plus irrational numbers, so therefore we need to talk about what rational and irrational numbers are. First off, you have irrational numbers. We see here by definition it says a rational number is any number that can be written as a fraction. This includes terminating or repeating decimals and the following sets, which we'll talk about in just a second. So therefore, if we're talking rational numbers, let's just list some of the examples of rational numbers. Again, it does include fractions, which it does include mixed numbers as well. Includes terminating and repeating decimals, which a terminating decimal is a decimal that it just stops, it doesn't continue, like 7.8, and a repeating decimal therefore would be something that does continue, maybe like 6.3 with a bar over it, 6.3 repeating. It also includes, like it says, the three sets, which is listed below. The natural numbers, which you see a lot of overlap in these three things. See, the natural numbers, another name for this is the counting numbers, or the numbers that you started out learning, the numbers that came natural to you, or the numbers that you started learning to count by. The natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth. Then you have the set of whole numbers, which if you notice, there's a lot of similarities between whole numbers and natural numbers. There's only one difference actually, and that's the number 0. The whole numbers, I remember it like this: the whole numbers start with a whole. You see that 0 does look like a whole, so therefore that's the only difference between the natural numbers and the whole numbers. And then you have the sets that's called integers, which the only difference between the whole numbers and the integers is that you have these negative numbers also included. So it includes all the negative whole numbers, I guess if you use that term loosely, all the negative whole numbers, 0, and all the positive whole numbers. So that's all your rational numbers. So therefore, if we go back to our list, we could also include numbers like 0, 3, -5, and so on and so forth. So again, a rational number is any fraction, terminating or repeating decimal, any whole number, any which again 3 is also a whole number, but also any counting or natural number, and any integer, or all these are rational numbers. The next group we're going to talk about are called the irrational numbers, and if you think to your English lesson, the IR at the beginning of this simply means not. So an irrational number is any number that's not rational. So if you think about the list that we've created here, and think about anything that's not included in this list, and we've included most everything, but there are some numbers that aren't rational. These numbers include anything, any decimal, I guess you could say, any decimal that does not repeat or terminate. So any non-terminating, non-repeating decimal. Some examples of these you might remember back from junior high school, the number pi, which is about 3.14159, and we do know it continues on and on forever, and it never follows a pattern. Later on in this book we'll talk about the number e, which is 2.718, and it's a lot like pi. It keeps going on and on forever and never repeats. The other most common irrational numbers that we run up on is any square root that's not a perfect square root. And when I say that, I'm not talking about the square root of 1, because we know the square root of 1 is 1, which is a rational number. The square root of 4 is 2, that's also a rational number. The square root of 9 is 3, that's also a rational number. I'm talking about these other square roots that we don't have a perfect root for, such as the square root of 2, that's not a perfect root. The square root of 3 is not a perfect root. The square root of 5, the square root of 6, the square root of 7, the square root of 8, none of those are perfect roots, so therefore those are also irrational numbers. So what we can now do is actually create somewhat of a Venn diagram to represent all these real numbers. And again, real numbers is the set of rationals and irrationals all together. and that does include most numbers that we will talk about this year. There is another type that we'll discuss later on. So you have the real number system. If it's real, then it has to be one of these two things. It's either going to be irrational or it's going to be rational. If it's rational, it could be an integer. If it's an integer, inside the group of integers you have the whole numbers, and inside the whole numbers you have the natural or counting numbers. So therefore there's what the groups look like in a diagram. And again, over here with the rationals you have numbers like pi and e, the square root of 5, the square root of 2, and so on and so forth. Rational numbers, think about rational numbers that's not inside one of these other sets. Could be like 0.3 and 7/10 and things like that. Integers, think about an integer that's not a whole number or a natural number. Would be like -3, -7, -5. Your whole numbers that aren't natural numbers, well, actually there's only one that's not a natural number, and that's 0. Then your natural or counting numbers are like 1, 3, and 7, and so on and so forth. The next thing we're going to discuss in this section is graphing, and I'm not going to go into great detail in this. Hopefully it's something that you remember from math classes past. But anytime that we're graphing, we're talking about two-dimensional graphing here. We're talking about graphing what's called ordered pairs, and we graph on what's called the coordinate plane, or the Cartesian plane, named after the founder of this graphing system. And again, this is a two-dimensional graphing plane. We're only graphing left, right, and up and down. There is a third dimension that we'll talk about later on in the book. Whenever you do have this type of graphing, you have two what's called axes. You have the y-axis, which runs vertical, and you have the x-axis, which is the horizontal axis here. These two axes, when they cross, does divide your Cartesian plane into 4 quadrants, and we most of the time denote these with Roman numerals, and these go counterclockwise, starting with the first quadrant in the top right, the second quadrant the top left, the third quadrant bottom left, and the fourth quadrant bottom right. Those are your 4 quadrants. And again, I told you that well, before this, these two things cross. The intersection of the quadrants is what's called the origin. And the origin, the reason we call it the origin, an origin is a starting point, the starting of something. And anytime that we're graphing ordered pairs, and again, the reason we call them ordered pairs is because there's 2 of them. There's a set, there's an x and a y. So whenever we're plotting these points, the x comes first, and the x tells you left or right. The y comes second, it's your up and down point. So therefore, to graph the point 6, 3, if it's a positive, we're moving to the right. If it was a negative, we're moving to the left. So again, the first number is your left, right. The second number is your up, down. If it's a positive, we're going up. If it's a negative, we're going down. So since both of these are positive, this means that we're going to travel right 6 and up 3. So we're going right 1, 2, 3, 4, 5, 6, and we're going up 1, 2, 3, and we're putting a dot there. Again, notice where I started at the origin. So that's the point 6, 3. If I wanted to plot the point negative 3, 4. Notice again our first number is negative, that's your left right number, which since it's negative we're traveling left 3. Since the second number is positive, we're going to go up 1, 2, 3, 4. So there's the point negative 3, 4. We'll plot one more of these for you. We'll plot the point 3, negative 5, which again, first number being positive, second number being negative, that means you're going to move to the right, and then the second number negative means you're going to move down. So we're going to go to the right 1, 2, 3, we're going to go down 1, 2, 3, 4, 5, and there's the point 3, negative 5. The only quadrant we didn't graph in is this third quadrant, which obviously in order to get a value in the third quadrant, both x and y should be negative. So therefore, the only other ones that might give you trouble is if you have a 0 mixed in. -3, 0 tells you're going to travel left 3, but you're going to go up 0, so you're actually going to stay put on that x-axis. Or if you had 0, 7, that first number tells you you're not going to travel left or right any, but you are going to travel up 1, 2, 3, 4, 5, 6, 7. So that would be the point 0, 7. We'll now go over a few more definitions that'll appear throughout the textbook throughout the year. The first one being a scatter plot, and we'll talk about this much more later on in this chapter. It says a scatter plot is a graphical representation of a group of points used to determine if there's any relationship exists between the input and the output, or the x and the y. And a scatter plot it's just a group, a set of points, just several points, and we can actually graph the plot or graph the points. And it might just look like it's scattered, like you just threw a set of points. You just threw several points on the graph, and that's what it is, hence the name scatter plot. And we can look at it and a lot of times determine if there's a representation between somebody's height and their shoe size, or if there's a representation between some x and y set of points. The second, again something that will occur several times during the book, is the domain. The domain is simply the set of all x values, or another name for the x values are the independent variables in a relation. The range is right the opposite. It's the set of all y values, or the dependent variables in a relation. But notice in both of those definitions we use the word relation, and relation is just any relationship that exists between two sets of numbers. It's the connection between the two. Maybe your y's are going to be one more than all your x's, or maybe your y's are going to be twice as much as your x's, but it's some relationship between the x's and y's. It says relations can be represented by a set of numbers, or a set of points. In that case, we can represent it with a table, a rule, a mapping, or a graph, several different ways, which we'll demonstrate, I believe, in this next example. So given the following relation, and we see here 0, 0, 1, 1, 1, negative 1, this relation is actually represented this first way. It's represented by, that should say, a set of points, because it's not just a set of numbers, but the numbers are actually points. 0, 0 is a point, 1, 1 is a point. It says state the domain and range. So let's transfer this over so we can do this problem. And here are our set of points. And the first thing it asks us to do is state the domain and range. And here's how I would like for you to do that. The domain is equal to, and the domain is a group or a set. The domain again is the group of all the x's. So all you've got to do is go down through here and find your x's. And when we're stating the domain, we don't have to state those x's more than one time. So what we can say is the domain is the set 0, 1, 4, and 9, and that's all of our x values. And the second thing it asks us to do is find the range. And the range is again simply all the y values. And notice here we have 0 and we have 1 and negative 1. We do have to list both of those. Those are two different numbers. We have 2 and negative 2, and we have 3 and negative 3. So the range is the set of all the y values. It then tells us to graph all of our different points, and let's see if we can draw a graph for it. And the way I start out my graph, I don't draw a large x and y axis. I just draw a small starting point, and I just draw my origin. And let's simply graph all these points. Our first graph, or our first point, is at 0, 0. That is the origin. Our second point's at 1, 1, so we're going to go right 1 and up 1. Our third point is 1, negative 1, so you go right 1 and down 1. Our fourth point is 4, 2, so we go right 1, 2, 3, 4 and up 2. Our fifth point is 4, negative 2, so we go right 4 and down 2. Our next point is 9, 3, so we're going to go right 1, 2, 3, 4, 5, 6, 7, 8, 9 and up 1, 2, and 3. And 9, negative 3, we'll go right 9 and actually down 3. So this is a set. If we're simply graphing these xy values, these points, that's the set of all of our points. Up here we have 7 points. Down here we have 7 points. We don't have to connect our dots or anything in this case, because we are again simply plotting these points is what it asks us to do. The next thing it asks us to do is actually draw a mapping, and mappings are easy to do. Let me show you what a mapping is. We're going to make a list of all of our x's down through here, and our x's were 0, 1, 4, and 9. And then we're going to make a list of all of our y's underneath here, and I'm actually going to put these in order. Our y's were -3, -2, -1, 0, 1, 2, and 3. And then we just draw arrows from, like, our first point was 0, 0. So when x was 0, our y was also 0, so we just draw an arrow between those two. When x was 1, y was 1, so we draw another arrow from 1 to 1. Our third point was 1, -1, so we draw an arrow between those two as well. Notice we have two different 1s coming from 1 because 1 was paired with two different things. We had 4 paired with -2 and +2. We had 9 paired with -3 and +3. So that's all a mapping is just drawing arrows from your x's, or from your, again, another name for that was your domain, to your range. And finally, the last thing they asked us to do was to actually find the rule that carries us from x to y, and sometimes this is a little bit tough to just look at, which we can on this one, but sometimes it is hard just to look at to find the rule. But going from 0 to 0, and going from 1 not just to -1 but also +1, and from 4 to -2 and +2, and 9 to -3 and +3. It wouldn't be as hard if we were just going from 4 to 2, and from 9 to 3, and from 1 to 1, and from 0 to 0. But since you throw in these other ones, that makes it a little bit more difficult. But I do notice something about a square root. I know the square root of 9 is 3. I know the square root of 4 is 2. I know the square root of 1 is 1, square root of 0 is 0, but the negatives as well. And here is one way, and this is a symbol we're going to use a lot this year, that we can use. We can say that y is not only equal to the square root of x, because it is. This y here at 1, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, but not only the positive but also the negative square root of x. So this is our rule, that y is equal to the positive and negative square root of x. So that's saying, like, when x is 9, then y is equal to positive negative square root of 9, which is 3, so y is equal to positive negative 3. When x is 4, then y is equal to positive and negative 2, and so on and so forth. Next up, we're going to talk about the concept of a function, and we see here the definition of a function. It says a function is a relation where each element of the domain is paired with exactly one element of the range. We can also say that each x has only one y. Notice in example 2 it says tell whether each is a function. In 2a here, -2 is paired with 2, and we can look down the list and -2 is not paired with anything else, so we're okay there. 0 is paired with only 3, 3 is paired with only -2.5, 1 is paired with only 2, and -5 is paired with only 4, so therefore yes, the first one is a function. Looking at the second one, again I remind you each x can only be paired with a single y. 0, we're looking down the list, 0 is only paired with 1, that's fine. 1, we look down the list, 1's only paired with 1, 2's only paired with 1, 3's only paired with 1, and the same way with 4, 5, and 6 is only paired with 1. And even though the 1 is paired with each of the different x's, that's perfectly fine, because as long as each x is only paired with a single y. In C, 0 is paired with only 0, we see that, but we have a problem right here. 1's not only paired with 1, but 1's also paired with -1, and we see the same thing with 4 and the same thing with 9 here, so therefore no, C part is not a function. Next up, we're going to talk about function notation, and we see here kind of a definition of a function notation, what it actually is. If a relation is a function, instead of using like y equals the rule for the function, we can use function notation, which this is read as f of x, is how you read that. The letter is the name of the function, and the second letter simply tells you the independent variable for the function, f of x, probably the number one mistake made, f of x is not f times x. It looks like it, but it's that's not what that means. Again, instead of y equals 2x, we could say, think of it like this, instead of y equals 2x, we're saying f equals 2x. To where when we see that f, we realize it is a function, but we don't use just f. That's what I wanted to get, point I wanted to get across to you. We put an f and then we put the x in parentheses, just saying that instead of f equals 2x, we're saying that f is a function of x. That x is the independent variable in the function. So again, instead of writing y equals 2x, we can write f of x equals 2x. Which again, like I was saying, is the same thing as just saying f equals 2x. Don't let the x in parentheses throw you off. Second part says if f of x equals 2x, then f of 3 is simply asking us to plug in 3 for our independent variable. Notice that we have a 3 in the place of the x. So all that says, when you see that, all it means is wherever there's an x in your statement, plug in a 3. So therefore f of 3 would equal, instead of 2 times x, it equals 2 times 3, or 6. So therefore f of 3 is 6. Example 3 says r of x is equal to the square root of x plus 4 minus 2. It says find r of 5, r of 2, and r of a plus 2. Again, the problem asks us to, or tells us that r of x, and notice again, on the problem before we had f of x, and we can use f, g, h, r, s, t. We can use any letter in the place. It's just a name, is all it is. Instead of like y equals the square root of x plus 4 minus 2, we're just saying r. So no big deal there. We can use any variable. So r of x, which again x is our independent variable, is equal to the square root of x plus 4 minus 2. In order to find r of 5, all that says is anywhere we have an x, which right there is the only place, anywhere we have an x, just put a 5 is all this means. So we now have the square root of, instead of x plus 4, we have the square root of 5 plus 4 minus 2, which is equal to the square root of 9 minus 2, which is 3 minus 2, which is 1. To find r of 2, r of 2 is equal to the square root of 2 plus 4, square root of 2 plus 4 minus 2, which is equal to the square root of 6 minus 2. And if we can leave that as an exact answer like that, or we can take out our calculator and actually calculate the square root of 6. Let me get the calculator. So here we go. Let's type that in. We have the square root of 6, and to get an approximate answer on that, well, there's this approximate answer, and then we got to do that minus 2, enter. So we have r of 2 is equal to about 0.449. We'll round it off to 3 decimal places. And finally, on the last problem, we have r of a plus 2. And again, what that means is anywhere we have an x, we're going to plug in a plus 2. So we have the square root of, instead of x, again we put an a plus 2 in the place of x. So we now have the square root of a plus 2 plus 4 minus 2, which can be simplified into the square root of a plus 6 minus 2, and we can't combine any more like terms because the 6 is underneath the parentheses, or underneath the square root, so that's all we can do with that problem. So therefore the r of a plus 2 is equal to the square root of a plus 6 minus 2. Okay, the final example here actually gives us a graph and asks us to answer questions about the graph, and you see here's our origin. I'm going to highlight just so we can see it better. First off, it says what is the domain of the graph, and again, domain is the x values, the left and right values. So pretty much when it's asking for the domain, it's saying how far left does the graph go, how far right does the graph go. So what we can see is I can kind of draw a dotted line. That's how far left the graph goes, and I can draw a dotted line here. That's how far right the graph goes. So therefore the domain of the graph, it comes from, we can count over 1, 2, 3, 4, from -5 is where the graph starts, and it goes up to 1, 2, 3, 4, 5, 6. So therefore we can write that as x is between -5 and 6. That's a good way of writing the domain, and we'll talk about later on, I believe actually in possibly the next chapter, another way to write this. The range of the graph now is how far up and down the graph goes, because again the range is your y values. It's what values of y is represented by the graph. We can see this is how far down it goes, and this is the highest point on our graph, and I feel like this is the easiest way to do this. So there's how far up the graph goes. So again we can count down and we see that that's -3, and go up 1, 2, 3, it goes up to 4. So therefore our range, our y values range from -3 up to 4, so we can write that as -3 is less than or equal to y is less than or equal to 4. So therefore there's our range on our graph. Next problem asks us what is f of 3, and these are pretty easy. That's simply saying when x is 3, what is the function equal to? That's what, if you remember the function notation, the whole f of x, when we plugged in 3, that's what we plugged in 3 for x, is to find out what our function was equal to. So in order to find f of 3, all we got to do is go over to 3. There's where x is equal to 3, and then we go up to our graph, and we see that when x is equal to 3, there's what our graph or our function is equal to. So if we count over to 3, we go up, our function is actually equal to, we go up 1 spot, so f of 3 is equal to 1. F of -2 is a little bit different because of, if we go over to -2, if we actually look at our curve here, we have an open space at -2. And if not for, we've also got this point down here. If not for that point down there, our graph would actually be undefined because there's no value there at -2. And if not for the dot down here, then our function would be undefined, but it is defined. When x is equal to -2, our y is equal to this down here. Our y is also actually equal to -2 as well. And the last one, or E part, we're asked to find f of 6. So let's go over to 1, 2, 3, 4, 5. When x is equal to 6, then our function is equal to this right here, which is, let's see, that's -1. Okay, the last one says what value of x gives makes our function equal to 4. So we got to see where's our graph equal to 4. Where's the highest point at? And it's kind of hard to see, but it actually, I've got a dot there on the graph to where we can see it comes up and it touches right there, and then it starts coming back down. So let's see, if we go over, that's actually right here. So f of 1 would equal to 4, so therefore it's equal to, f of x is equal to 4 at x equals 1.